So today we're very happy to have Victor Rodriguez from Princeton University, who's going to be telling us about the two-dimensional string cosmology. Please, Victor, take it away.
So thanks. Let me begin by thanking the organizers for the opportunity to speak here, tell you a little bit about the work I've been doing over the past few months, which concerns a two-dimensional string cosmology. So it's going to be a time-dependent background, string theory background that nevertheless admits an exact worldsheet description. So thanks for having me. It's a pleasure to visit Chicago, and especially to these audience to talk about this string cosmology. Okay, so let's get started. Okay, so here's a brief outline we'll talk about. First, I'll give a brief review about two-dimensional string theory. I suspect that for a large part of the audience here, this would be a basic review, but at least it'll set up the language for what will be the story about the two-dimensional string cosmology background, which will be the next point. And right after that, we'll jump into computing some of the simplest observables in this string theory, which will be cosmological wave functions, and I'll come to what that means in a second. And explicitly, I'll show the computation of a couple of simple observables, like the 3-point, 4-point sphere diagram, as well as the torus 1-point diagram. And then right after that, we'll see how these combine to contribute to a given cosmological wave function. And as you'll see, there's still plenty of open questions that we'll finish with a discussion of those and future prospects. Okay, so let's jump right into it. So, but before, let me just give you a few highlights of what two-dimensional string theory is, just to remind you a little bit. It's also known as C=1 string theory. So it's a bosonic worldsheet theory. So it's nice, and there's no supersymmetry either on the worldsheet or in spacetime. So less moving parts. So it's a bit simple. It's also a theory whose target spacetime is two-dimensional. So it's also simple in that regard. And for example, there's no infinite tower of massive string states. In fact, there's only one propagating degree of freedom in spacetime, and it's just that of a massless scalar. So it indeed very simple in this sense. And of course, one of the most important reasons this was an important model in string theory is that it was discovered to be dual to matrix quantum mechanics in this famous inverted quadratic potential, inverted parabola. So it's one of the earliest examples of holography that we're studying in the string theory community. Okay, but today we won't talk too much about the matrix quantum mechanics. So if you're a bit rusty on that, don't worry, we won't discuss that too much today. Okay, but let's in more detail, let's discuss what this two-dimensional string theory is. As a reminder, so we got a time-like free boson, which is interpreted as time. We got C equals 25 Liouville CFT, which is interpreted as space. It will give it a name for its field, phi, and the usual BC conformal goes. So the total center charge of the system is 0, and we have a critical string background. Okay, but let me perhaps the slightly unfamiliar piece here is Liouville CFT. So let me describe that in a little bit more detail. And let me take the sort of the bootstrap approach of the definition of the CFT in terms of its operator spectrum and 3-point coefficients. So I'll describe that in the next few slides, and we'll come back to its interpretation in the following slide. So to specify what the CFT is, for those who are familiar with Liouville CFT, with the parameterization of the background charge Q, and this is related to center charge like this in gray, and the background charge related to the Liouville potential B in this way, the relevant value here is B = 1. So for those who are familiar with the DOCC formula and so on, this is a limit in which things simplified a little bit, not a ton, but a little bit. So okay, so the spectrum, the first piece of data is what's a list of operators of the theory. So they come in a continuous family of scalar versus solar primary, precisely of this way, 1 plus p squared, where p is just a real number, colloquially called the Liouville momentum. You can think of them, at least in the asymptotic region, as just describing this. I'll denote all these scalar versus solar primaries as VP abstractly, but you can think of them as plane waves, shifted by the background charge Q, which in this case is 2. Okay, so very simple, just scalar fibers. And the other piece of data I need to specify is the 3-point coefficients. So it's here, it's a celebrated DOCC formula, and I'll write it here in gray. So you shouldn't pay too close attention, but just to say that it's a very explicit formula, and we know its properties, and it is written here. Okay, but just want to emphasize that it's a very concrete CFT, and in principle, any correlation function, and this C equals 25 of the CFT, and therefore, as an ingredient of the full string theory that of the previous slide, you can compute any scattering amplitude in this theory. So very explicit. Yes,
This is true for any C, right? Or
yes, it's true for any C, but so this equals 25 is the one that's relevant for two-dimensional string. Yeah, and yeah. So the only thing that simplifies a little bit is this epsilon function, which is a little simpler in this way, but still complicated as this form. Okay, so it's not very important to know what the function is, but something that will be relevant a little bit later. It's its analytic structure of the DOCC formula for fixed P1 and P2, two of the momenta, and in the complex P plane. So this is relevant, for example, the composition of the 4-point function in terms of this 3-point coefficients, like this in this picture. And the only thing I want to point out is that the structure of its poles are in this like 4 vertical lines. And for instance, all these poles happen at, depend on what these two P1 and P2 are. So P1 plus P2 plus a non-zero integer. And this is the analytic structure. And this is not important right now, but it'll be important later. And again, this is relevant if you want to compute a 4-point function. You decompose it into the two DOCC structure functions here, C and C, and an appropriate Virasoro conformal block integrated over the intermediate state of momentum, which is integrated above this real axis. Okay, so very explicit.
can you remind us, since we're talking about explicit, those blocks are not known analytically, though, are they?
Not analytically, but there are recursion relations that's in practice what we'll use. You can compute it to basically arbitrary precision. So this for practical purposes, these are basically known. Okay. And so now putting things together. So I just described the CFT piece, but now building the string to find the physical states. You have to build 1,1 vertex operators from our ingredients, and here they are. So the conventional factor of G string, plane wave in the time-like free boson, which we're familiar with, and then one of these abstract Liouville vertex operators, such that its Liouville method is in my convention is omega/2. So this whole thing is weight 1,1, and these are the massless scalars that I mentioned in the first slide. Okay, so simple as that. That's it. There's no infinite power strings, just these, and so those are the physical states. So in the previous slides, I emphasized the bootstrappy definition of the internal worldsheet CFT, but let us look at the worldsheet action just to get an intuition of what the space-time physics is. So here I wrote the Liouville action, Liouville field phi. So it takes this form, some kinetic term, linear dilaton term, and the famous Liouville exponential wall. For our cases, Q is 2 and B is 1. So the first thing to notice is that there's a linear dilaton term, and as a consequence, the string coupling is since this is going to be interpreted as a space direction, the G string, the string coupling depends on where you are in space. So when phi is very large and negative, we have very weak coupling, and then the opposite extreme, where phi is large, we have very strong coupling. But then this is the purpose of this third Liouville potential is to shield you from this potentially strongly coupled region like this. Okay, and the vertex operators I wrote in the previous slide, these massless scalars are something that coming from the left, from the asymptotic region of weak string coupling, come up here, interact where the string coupling is non-zero, bounce off the wall, and then go back to infinity. That's the main physics of this model. Of this stringy description. Okay, so there's another picture I like to keep in mind. So here is space, the Liouville field phi, and this is time, the free field x0, and the atomic energy is on this side. And you have incoming string states that come in, interact, bounce off the wall, and go back to infinity in this way. So just as a reminder, here are examples of S matrix elements that we can compute in string perturbation theory. So here are two examples, for example. The one that is pictured here is the 1 to 2 scattering amplitude, so 1 incoming and 2 outgoing. And well, even though the internal CFT was fairly complicated, the DOCC formula, the actual scattering amplitude is fairly simple. In this case, it's just the product of the incoming energy and the outgoing energies. So the product is another example, so maybe slightly more non-trivial because of this piece, but they're simple. Okay. And for example, you can check that these scattering amplitudes do agree with the proposed matrix quantum mechanics too. Okay. And this is some work that I, for example, did with the past few years with Bruno, who's here in the audience, and with Xian at Harvard, including non-perturbative stuff from the instantons. Okay, and there's many references to this that I did not attempt to provide here. And sorry for that. Okay, but these are two examples. So, and this is supposed to remind you of the matrix quantum mechanics picture if you're familiar with that, but we won't discuss it further. So this is a good place to stop. If there's any questions before we go into the cosmological background.
I just want to follow up on the thing on the last slide. So worldsheet string perturbation theory can be used to compute what exactly here?
Oh, this matrix elements.
But they're not very sensitive to this strongly coupled region.
Yeah, no. So it's shielded by this bundle. So
But the higher energy you put in, the higher you would go into this region.
But that's a magic of
So wouldn't you expect that it's less accurate for high energy scattering amplitudes?
No, it's supposed to be exact. So the full solution of the intrinsic worldsheet CFT has that information in it. And so you could say, so the action that I wrote down, you could treat that perturbatively, the worldsheet action of Liouville. And that would suffer from precisely that. If you wanted to do a 2D QFT on the worldsheet, that would suffer from that. But the bootstrap solution is supposed to include all these effects.
I see.
Okay. All right, so let's jump into the cosmological background now. So again, let's start again with time independent one, the one that we just described here, and we'll do a very simple modification to this. We'll replace the free piece, the time-like free boson, by an interactive piece, namely C+1 Liouville CFT. Okay, so I already described in some detail what this looks like. Now let me describe what this is. There's going to be two Liouville's in the game, so hopefully it won't be too confusing. Again, so if with the usual more general parameterization Liouville CFT, which is again repeated here, if you want the center charge to be 1, seems like you want to take this Liouville parameter B, which controls the potential, to be imaginary, and precisely I, so that C equals 1, and Q equals 0, and C equals 1.
So it would not be unitary.
It would not be unitary. Well, unitary in the space point of view. As an internal CFT, it's a unitary CFT, as we'll describe in a second. Yeah. So naively, you would think, okay, just take DOCC formula and analytically continue to be equals to I. So that's what some part of the literature did, but the main upshot is that it turns out that this procedure is incorrect, precisely more generally along this branch of the imaginary values for B, which corresponds to central charge less than or equal to 1. The relevant here is equals 1, but more generally is the case. So for example, the epsilon functions in terms of which this was described or written in terms of diverges in this limit, naive limit. The upshot is that you have to reanalyze the bootstrap equations, and it turns out it gives you a different solution, which I'll describe in the next slide. Yeah.
Can you remind me just taking B goes to 1? Doesn't the DOCC formula also diverge? But there's some renormalization you need to do as well.
Yeah, that's some.
It's different.
Yeah, that's a different thing. Yeah. In fact, if you take the C+1, you have to do the same thing. In this case. But that's a different, it's a more serious thing that you can't just absorb into the vertex operator.
I see.
Normalization.
I see, okay.
Okay, but let me now describe in more detail what this is. This is what the key points will be. Again, let me give you the two pieces of data of the CFT. And just to avoid confusion, whenever you see a hat, it will refer to the C equals 1 that will eventually be the time leg piece. So hats are for the time leg piece. So again, the spectrum comes in a continuum of scalar versus primaries. But now with this way, so Q is 0 in the relevant limit. So it's just P squared. Again, labeled by real momentum, so-called Liouville momentum. So let me label them abstractly as V hat P. Okay, so it's the same thing. And it's 3-point structure constants. It's a different one, that's the point. And it's written here explicitly also in terms of this epsilon1 function, but in particular it's different from the first DOCC. So let me call it DOCC number 2 for concreteness.
How is this formula derived?
Same tricks as the other one. Now there's a key to get into the technical aspect. There's a key assumption that it's not valid for this case. So usually it's called Teschner's trick. And what you do, you put in the 3-point function or 4-point function, you put in the general representation into the 4-point to derive a differential equation for the correlator. And at some point in that step, you use the degenerate representation with weight 0 is proportional to the identity. And here the key point is that that's not necessarily the case. It could be a non-degenerate representation with weight 0. And that possibility leads to this second option. So it's slightly technical, but the main point is that you get this second DOCC function, and as I'll see in the next slide, it gives a well-defined CFT.
So
that
P
obeys cross.
P equals 0 here does not lead to the identity? Well, what's
sorry.
the primary that can have weight 0?
So that's the point. It could be the one that is P equals 0. More generally, it won't be this one, but this is one. So it's actually not even this one because this would be the non-degenerate representation. It's technically in Teschner's trick, you input something that is not in the actual operating spectrum. That's why it's a trick, not rigorous derivation. But it's one that has weight 0. So is the 1,1 degenerate representation of the Virasoro algebra. For the DOCC number 1. For DOCC number 2, the point is that it's still a weight 0 operator, but it's not the 1,1.
None of these operators are in the spectrum?
Yeah, no.
Why do you get a correct differential equation?
Well, that's a good question. The point is that I think my point of view is that okay, you do this trick, you derive some 3-point function, and then you check. Whether it leads to a well-defined CFT. That's my practical point of view. I mean, it's not a mathematical.
Usually when we solve with the minimal model, we get the equation from an actual operator.
Right. That's because we are interested in degenerate representation of the minimal models. But here, we're only interested in the non-degenerate ones. But somehow you still get, this trick still works. Like, I'll take the point of view that, okay, it's some trick that outputs some potentially well-defined 3-point function. Now let me check if it's actually well-defined. And I'll check that in a second. Okay, so just to make the point clear, so that its analytic structure for big P1 and P2 and on the contour P hat plane, it looks totally different. Instead of being like 4 vertical columns, that's what the usual DOCC is, it actually just slides out in the real axis. So in particular, it actually doesn't depend on P1 and P2, it just lines at half integers. And of course, this is relevant again for if you want to compute a 4-point function like this, decompose it into conformal blocks, like this. And actually, this one last piece of data I need to tell you. If you want to decompose it this way, you have to integrate with intermediate state with momentum P hat. Usually we take the real one in the axis, but there's a bunch of bolts there. But so the contour of integration for this decomposition is the following: is this one, the easiest thing it could be. So just you can think about it as an I epsilon contour. Shift vertically a little bit to avoid the poles and do this integral. With this prescription, you can check, for example, that this function expanded like this is crossing symmetric. And that crucially depends on the form of these C's. So that's my practical approach. With this new piece, you still get a well-defined 4-point function and also a torus 1-point function, which by cutting and sewing, you can know that it makes sense on every random surface. So that's
This is a unitary 2D CFT.
Exactly, it's
with
unitary.
continuous spectrum and no vacuum. Is that correct?
That's correct, yeah. That's the same for the usual
Yeah,
space.
yeah. Just trying to understand in what way it was different.
Okay. So that would be a key ingredient, satisfying crossing and so on. Okay, but as you mentioned, this is a Euclidean CFT. Okay, so one last step to define the string cosmology is that we want to have a Lorentzian theory. So what we want to do is analytically continue the Liouville momenta P to imaginary values so that we can interpret omega as an energy. Now we have to make sure this makes sense. It's not just doing naive, but just for the remainder of the slide, suppose that makes sense. Then we could build the usual vertex operators. So instead of a free piece like this and the usual time-independent C=1 string, so now you have one of these vertex operators B hats with an imaginary value omega, and the other one dressed by the same value of omega, so that this has weight 1,1. And the whole point is that the dispersion relation is basically the same, that of a massive scalar. Okay, like this, thanks to that continuation.
Can you clarify what it is that you have to check to make sure that it makes sense?
Yeah, that will be in the next slide. Yeah. But crucially, this is only for external onshore states. So for these guys. Okay. So what I mean is that, okay, so we want to continue these guys more generally for any correlation function, but for example, this 4-point function, we want to continue this guy, this guy, this guy, so on with me. You guys in blue, and I want to have still a well-defined 4-point function. So I'm allowed to deform this contour, just to preserve analyticity as I continue these. And so we have to analyze what this happens. Okay, so there's a lot of things that are actually being continued, even the external ways here in the conformal blocks. But the crucial property of this second DOCC formula is that, as I showed you, the poles are actually independent of P1, P2, and P3 and P4. The continuation is rather trivial. You don't have to do anything. So you can do this without having to do extra work. Now, this is crucial. If you wanted to do this with a space like Liouville, this will be much more complicated because those poles do depend on P1 and P2, and they will start moving, crossing contour, and all this complicated things. So this is a key property that was already noted by Bautista, Doublecoat, and Urban a couple of years ago, that this continuation is rather trivial. That's what I mean. And also you can check that same is true, for instance, the torus 1-point function with the same contour prescription, and the continuation is kind of trivial. Okay. If you're a little worried, you can again, check crossing of this thing. I mean, it should be clear by this argument, but you can again check crossing symmetry, and it is satisfying. Okay. So back just to reiterate. So these are the asymptotic states, the physical states of a string theory with this continuation here to Lorentzian signature.
What's special about 2D string theory in doing this?
Exactly. Not much other than that. We'll come back to that in a second, but it's just the simplest example I wanted to play with where I can study this in detail. There's nothing intrinsically special about two-dimensional string. So in fact, you could take this C=1 and couple it to 25 free bosons, so you get a bosonic time-dependent string. Well, that still has a tachyon, so that's a different problem, but you can find the supersymmetric version of this C=1, couple it to the usual superstring, and that would be a time-dependent superstring. But unfortunately, that supersymmetric version has not been bootstrapped, but there's something to work on in the future. That would be extremely interesting, 10-dimensional superstring with this time dependence. But here you're just trying to find the simplest example that we can study it. But on that point, just to answer, another motivation for studying in this context is that hopefully this has a matrix model descriptor. It's easy to identify. That's another reason why I wanted to study in this context. And we'll find some evidence that that's the case. But we'll get there. Okay, but let's go back to the just a semi-classical action just to get a feel of what's going on in spacetime. So here I wrote down again the Liouville action for this curly phi. And let's see what we're doing morally. So we have this. Now the next step is to continue to this b equals I. Except put a beta here, but beta is 1. So in particular, as we already mentioned, this q hat is 0. We still have this piece, of course. So one feature of this is that the string coupling, still depends on where you are in space, but at least it doesn't depend on time. It's time independent. So that's a feature of this model, thanks to this precise value.
Do we also have an e to the minus 2i phi term in the function?
No. So that's also crucial. So it's only a solution for this specific potential. One could wonder if there's such a exact solution to a CFT that has both, but that is unknown.
And the Hermitian conjugate of phi is itself?
Let's see.
Naively,
I think so.
Naively, the action looks complex.
Right. But there's still a further step, but yeah. The further step is that now we're gonna go to Lorentzian signature. And now, the purpose of this is to go to the usual long kinetic time on the worldsheet, so that it's interpreted as a Lorentzian coordinate, and then we end up with this time-dependent potential, right? E to the negative 2 chi naught. So this is the interpretation. Yeah.
So I remember McGreevy had something very similar with a sort of imaginary Liouville with this type of action.
Yes.
Can you comment on that? Or maybe it can also be after later.
Sure. Well, I don't remember exactly which paper you're referring to. I should say that at least I know for sure that paper predated the solution to C+1 Liouville, so they did not know about this second solution. So. Okay, so that's what's happening. And again, the picture I like to keep in mind is this, where again, draw space and time in this direction. The shaded gray region is supposed to represent the usual wall, the potential wall, the space-like one. But now in addition, we have this time-like potential, e to the negative 2 chi naught. And instead of having S matrix elements of strings that come in, bounce off, and go all the way there, what we have is only strings coming up in the infinite future here. So we have some initial state that it's implicitly defined by the worldsheet description. So that you can call it a Big Bang if you want. And so it's some initial state that somehow evolves in time. And then here it produces a particle production of strings in the infinite future. Here in the infinite future, remember the exponential potential e to the negative 2 chi naught just dies off. And here we recover the usual time independent background. C equals 1, the usual one. But here is something different. Yep.
What is like the boundary condition in the blue potential?
Yeah, so that's a good question. And my understanding right now is that that's actually implicitly specified by the background that you started with. So in this case, it's equals 1 Liouville cross equals 35 Liouville. If you hand me another C equals 1 theory, that would correspond to a different initial state. Okay, so there's some initial state in the past that we're probing in the basis of perturbative string states, the ones whose vertex operators I described in the previous slides. Right. So in this sense, it's a cosmological wave function.
The state is a function of what? What are the space-time fields? So when you say state, you think it's like a wave functional of some fields. What are those fields?
Yeah, those fields are the perturbative strings in the infinite future. The ones with some momentum omega that I call it. Some energy omega. So you're probing in terms of in this picture the three particle component of the initial wave function of the universe. So this it's just like the good thing to keep in mind, at least I think, is the usual case of time dependent QFT, where you have some state in the say infinite past that there's hopefully some natural vacuum. And in the infinite future, you have some other vacuum, in this case, the one of perturbative strings. So since there's time dependence, something is vacuum in one time is not going to be the vacuum one. It leads to particle production. So you're probing the vacuum in the infinite past in the basis of perturbed string states in the future. So for instance, this will give this one picture here will give you the 3 particle component of that wave function in the basis of perturbed strings. So this is the kind of
Your weakly lines only going to the upper left and not the upper right.
this is just because this is there's the spacetime wall.
But I don't understand. It was also there before, and you drew things coming in from infinity, bouncing off the wall.
They came in from infinity at the bottom left.
Yeah, for the infinite past.
So what?
Here in the infinite past, let me. Here in the infinite past, the potential is infinite.
No, I mean, I think you don't understand my question.
Okay.
So if you go up in your picture, if you go up in your picture,
Yes.
there is a region of very large chi0
You're going like
and
this.
phi that is not near the wall, where you can write whatever vertex operators you want. And in particular, you can write vertex operators that are moving to the left and ones that are moving to the right.
Yeah,
So
so
my question is, why did you not write the ones that are moving to the right?
I understand the question now. Thanks. Yeah, so perhaps this is not a super clear picture. The vertex operators for C = 1 Liouville CFD indeed have both components, one that is incoming and one is outgoing, right? So perhaps I should have said like some combination of going like this and going like this.
I mean,
but only
again, everything you just said was also true before,
yeah,
and yet you drew both components
right.
explicitly. You didn't just say, I don't need to write the second component because it's a piece of it's the reflected part of the first component.
Yeah, true.
So
No, I
if
think
you did it there, you should do it here. And
Yeah, no,
vice versa.
No, I think you're right. So it's a fair complaint for this picture.
I'm not complaining.
No, but you're right. The vertex operators do have both components, as you say. But yeah, so this is the picture I like to keep in mind. One would know that it's not perfect.
So you should have waves coming from here and bouncing back.
Not from
But you-
here, not from here, but maybe here. So the wave functional of an asymptotic states has both an e to the plus I omega t and an I minus omega e to negative I omega t here.
I mean, the important thing basically to say is that you specify the vertex operators that you're allowed to stick in when you are going to compute some path integral. You in any case specify them up and to the left.
Yeah.
So
And those
that's where you specify them, and you can put whatever you want there. The ones that are moving to the upper left, to the upper right, it doesn't matter. They're all living in the weak coupling region. So
and
I mean, they're not independent, of course, but they were not independent before this blue region made its appearance.
And in fact, it's important that it has both components because the coefficient of those, in terms of this initial wave state, are the 2 Bob coefficients, right? So it's important it has both components. Thank you for the question. Okay, so that's the main picture. So let's see what kind of observables you can try to compute. So bear with me for the next few slides, which will be slightly technical, but as you might imagine, this is where the most of the work is involved. So and then next few slides, I'll compute a couple of string diagrams, and then we'll put them together and see what kind of observable we use. So okay, the very first one, the simplest one that we can compute is a pure 3-point diagram like this, which is just computed by a 3-point function of the end of the line CFD. Like that, there's no moduli in this case after fixing the 3 positions. So it reduces to the product of the 2 3-point functions, the DOCC number 1 and the DOCC number 2. There should have been a minus sign in all of this. Okay, and then they're complicated functions, but it turns out that in the end, it does simplify again to something very simple. Again, just a product of the outgoing energies like this. Okay, so it's again the usual drastic simplification. But now let me, it's nice to contrast this to the time independent case. So again, I'll remind you what that looked like. The 1 to 2 scattering amplitude, which again took the same form. But let me stress that in this case, energy conservation, the delta function here, was totally crucial for this DOCC formula to reduce to this simple product. Now in this cosmological background, there's no energy conservation whatsoever. So this omega 1, omega 2, omega 3 are completely arbitrary. There's no relation between them. But somehow still after multiplying by this DOCC number 2, the result is that it does reduce to something simple again. So I just wanted to stress that there's no energy conservation, but yet it's still simplified to something simple.
The C of S is some normalization factor for the partition function.
Yes, thank you. So this, I want to attempt to compute. The CS2 is like the normalization associated with the sphere topology. So usually in time-independent string theory, these can be fixed through factorization properties of string amplitudes. But at least so far, I don't know what is the correct implication of unitarity. I don't know the the factorization properties of this type of observable. So I don't know of a way of computing these easily. So I'll just leave them as constants for now. Thanks for the question. And okay, so this might the simplification. You might think of maybe a first hint that there's a matrix model description. Just circumstantial evidence, at least so far. Okay, another example is slightly more non-trivial is a 4-point function. Now here all the ingredients that I was describing of the DOC structure constants are very important. But okay, I'll go quickly through this. Of course, just to give you a flavor of what it looks like, you have to compute two different 4-point functions. One is C equals 1 Liouville CFT here, and another one C equals 25 Liouville. So it's like 2 integral plus the integral over the moduli space. If you're interested, you can ask me how to do this in practice, but it can be done. So numerically, of course, since we don't have an analytic expression for the blocks, but you can do it numerically. I'll just flash you really quick some evidence for this. So you can, for some choices of omegas, you can compute them. Okay, some other slicing here for some arbitrary values that I chose here. And okay, so after collecting some data, perhaps the result is that even though it's a very complicated looking thing to compute, in the end it reduced to something kind of simple. Again, so the product of the omegas, okay, but then some constant, which is 7.5-ish, then beta, which is 50.99. Maybe you can guess what that would be, and then just the sum of the square of the omegas. Something very simple. Yeah.
So if I think of this as some sort of wave function, should I imagine these things are normalizable or not?
No. Oh, I see what you mean.
Square it, integrate over the energies. I mean, this doesn't look.
So only the full wave function, I think so. But what we're probing here are particular components. Oh, we'll come back to that. Exactly what we're trying to compute. But so far, I'm just doing string diagrams, and it's just in general a function of these energies. We'll come back to your question. If I don't answer it, please let me know. Okay, so some concepts, okay. So I take this as a stronger hint that there's still a matrix quantum mechanics dual, and it's a simple function. Lastly, just to flash again, in addition, you can compute the 1-point function on the torus. Okay, this is also not so pretty computation, but can be done roughly like this. So you have to compute two different 1-point functions on the torus like this, which if you expand torus conformal blocks, the different conformal blocks, curly H, against the structure functions again, using the same contour that I described earlier, and then integrate over the fundamental domain of the torus, so on. So again, this can be done. And okay, you get some data as a function of the outgoing energy, and the result again is something very simple. And here I didn't put any error because the error is super tiny, so I'm very confident that the 1/24 and 1/12. So then this is a much cleaner, it turns out, computation. Okay, so again, it's strikingly simple. I take this again as a sign of a matrix model dual, but okay, I don't know. Okay, so how do these combine to the actual observables? So to a given cosmological wave function. So again, this is a little bit similar to the instantons, in the sense that individual diagrams don't conserve momentum or energy. So again, there's no we expect that disconnected diagrams again contribute to the same observable. Okay. So for example, a class of disconnected diagrams or empty diagrams like this. And these have the property that they exponentiate nicely, just like the incidents do, like this, and they factor out of every diagram that actually has the insertions. The examples of which I computed in the previous slides. And yeah. So for example, the leading one, just by Euler counting, it goes as 1 over G string squared. This one goes to GF to the zeros, some constant, and this one gives you corrections suppressed by GS. Okay. So for example, let's do an example of the 1-point function. For example, the full cosmological wave function should look something like this. So next, the exponential of the sphere, exponential of empty torus, and then you have the sphere 1-point function. This goes as 1 over G string. So torus 1 point that I described in the previous slide goes as G string, the G string correction, and then the disconnected product of the sphere 1 point and the torus 2 1 points. Okay. Plus, of course, higher. Okay, so for example, one thing we can already write down. And this goes to 1 over G string squared. So some constant A that I did not attempt to compute yet, and this just some constant C. The factor of every possible cosmological wave function. So you can compute the once and for all, but I did not do that. But for example, this thing, we can already write down what the contribution for this is. Okay, and it looks like this by the answer that I wrote you before. There's still some constants that need to be computed, but of course, the empty sphere, as we know, it's kind of subtle to compute. Not sure, I don't think there's any unambiguous way of how to compute this. It will be a nice thing to try to do. And the sphere, the torus is also a little confusing, but we have not attempted to compute it and just call it some constant C to be determined. But then as a function, the actual thing that depends on the energy are the string diagrams, and this is the result. Now, you might wonder, okay, well, what about the leading one? So the leading one, the sphere 1 point. So if it were 0, then this would be the leading contribution. This would be okay. So what is the sphere 1 point? So of course, there's another example in which we don't have an unambiguous treatment of, at least in string perturbation theory. And the naive argument is usually this 1 point function is just 0. It's 0 because we have to divide by the residual volume of the conformal filling group on the sphere, which after fixing the position of this one vertex operator is still infinite. You have 2 more positions on the complex plane worth of freedom. So if you divide by something infinite, it's going to be 0. Furthermore, another reason to suspect that it's 0 is that the individual 1 point functions just at the level of the CFT, as long as they have a non-zero energy, so that means that these individual vertex operators have a non-zero weight. Just by scaling symmetry, just in this purely CFT, it would be 0. The 1 point function in the sphere would be 0. Okay. To me, this is kind of convincing evidence that this is 0. But I don't want to claim that it's precisely 0 just because I know at least one example in which it's been argued that this 1 point functions are non-zero. That's the case of strings in ADS3. The worldsheet description rate is 3 strings in the pure NSNS flux. That there's one special kind of vertex operator that's been argued by Jan Troost in the early 2010s that has a non-zero 1 point function.
How does it break these assumptions?
In that case, it's just that the actual the vertex operator there involves a divergence as well. It's like you're dividing infinity by infinity, leading to a non-zero thing. But that's the only example I personally know.
What do you mean in Liouville theory? The cosmological constant has a non-zero 1 point function. I mean,
right. You mean the cosmological, the actual deformation operator?
what you call the e to the 2b5.
Yeah.
This operator has a non-zero 1 point function.
Oh, I see.
Sphere. This is from when
Is
Jan
this-
Troost was in kindergarten, probably.
Does it does it lead to a non-zero string amplitude?
Of course. Well, look, the simplest way, I mean, the way you should have answered it, this question you raise here is the same as what it was answered in 1990, which is to take your 3-point function and to take the limit of two of the operators going to the operator 1, basically, if it's available. I'll say the DOZ formula, it has 3 operators. So you can take the betas as in e to the beta 5 of 2 of the operators to 0. And you will get a non-zero limit.
But then, okay, true.
And this business with all this stuff that you wrote here is known to be false in any theory which has a non-compact. Like both Liouville and ATS3 have a non-compact field space, and importantly, usually when we have a like saying a flat space. It's non-compact, but what we really are calculating all the time is the amplitudes per unit length. In other words, all the amplitudes we compute are proportional to the length of the circle or whatever. But in Liouville and ATS3, this is not true. It's non-compact, but on the other hand, there's no translation symmetry in the Liouville direction. In your case, both in the var-phi direction and in the other guy. And in ATS3, there's definitely no translation symmetry in the radial direction. And because of this, all these arguments that you write here were known to be false for like 30 years already.
Well, okay, so that's one thing what I did not try, but thanks for pointing that out. I should do that. One thing that confuses me, while we're at this point, is that you could have said the same thing about the time independent 2D string theory. So forget the time like these. And I think they're, even by not doing direct, but indirectly, if you try to see what this one-point function can be just by factorization of amplitudes, I think you can show that it has to be 0.
One-point function of what?
Of the vertex operators.
But with which omega?
With any omega, as long as it's not 0.
Well, okay, so for generic omega, the thing that kills it is translation symmetry in the time direction.
I see.
It carries non-zero momentum, if you wish. That's an example of it certainly is not 0 because of anything to do with Liouville. It's 0 because of the direction, the C=1 direction, the one with translation symmetry.
So the non-compact phase is just, okay.
Compact, non-compact. The point is that the thing that is 0 basically in that case is the term that goes like the length of time in the S matrix elements. This is what this kind of argument there shows. Now, if you have translations invariance in the time direction, then that's all there is processes that can happen at any time because there's no special time. But if you have a potential like e to the x naught, then of course, it's different.
Okay, well.
I mean, I'm not saying like in your case, 0 is not 0. This is a separate conversation.
Sure.
Just saying that
It could be not 0.
it's certainly not true that the first example in the history of mankind,
sorry,
the one-point function is not 0.
I see.
Yeah,
okay, thanks. True. So this requires further analysis. Okay, so let me not claim what it is. Just leave it at a question mark. I do have one suspicion, maybe physical argument for this. In this particular case, it might be non-zero. This is not it's not proof or anything, it's just a suspicion. But the suspicion is the following: is that to a given cosmological wave function, the leading order contribution would be the disconnected product of one-point functions. All right, and as we just discussed, this it goes to GS to the n, where there's n of these functions. This, at least in string perturbation theory, seems to be like a huge enhancement to this cosmological wave function, which grows bigger and bigger for higher input functions. To me, this seems the suspicion is that this seems a little bit unphysical. And for example, if you assume that this is the one-point function is actually 0, you can check that the leading diagrammatics actually leads to something that of order either 1 or order GS. So a bit more control in that way. But again, that's just a suspicion, not really a good argument. So let me not commit. Okay. So with that, so let me just show you what the actual wave functions will look like in some examples. So the diagrammatics are a little more complicated if we don't assume this is zero. So just for presentation, let me assume that this is zero just to show you what the diagrams will look like. And also let me factor out the exponential of the sphere and the exponential of the torus. It will look something like this. For instance, the cosmological one-word function has a leading contribution of the sort of one-word function that we computed, and then some higher corrections that look at this. The genus 2 surface with one insertion, disconnected product with these guys, and so on. Similarly, the 2-point cosmological wave function, the 3-point cosmological wave function, and the 4-point here. You can include more interesting ones. The 3-point here, and this one, so 2s. Okay. So that's what they look like. And these are the ones that I have computed thus far. So these guys. So if this turns out to be zero, then we do have some of the very leading ones, order ones. If the suspicion is right, then we do have. If not, then they become a bit more cumbersome. The diagrammatics are a bit more than this. Yep.
So just in pure Liouville, can't you just integrate the DOZZ 3 times and throw out? I thought
yeah, that's another
done, and they throw out sort of the analytic pieces, and the non-analytic piece is sort of the, like, even just for the sphere partition function, like the matrix model spit out an answer, and you can ask, how does the string theory know about that? And I think the answer is that you integrate DOZZ 3 times and throw out the analytic pieces.
Oh, I see. So you're saying that do the trick of differentiating with respect to the mu, the cosmological mu, and get something non-zero. Okay, that's yeah, true.
And again, that's been done.
Yeah, I see. Yeah, that's a good trick to try to compute this. Yeah,
especially if you have DOZZ already.
Yeah. All right. So thank you. So with that, here are at least some of the contributors have already been computed. Just to summarize. Okay, and since we're running out of time, I'll end here with a couple of concluding remarks. So, of course, some of the stuff that we already been discussing is a better understanding of this like lower point amplitudes, the 0 point, which we don't have an unambiguous way to compute. At least I don't know. There's one point function that we've been discussing already in the 2-point sphere diagrams, and also the torus. So that's definitely something that needs to be further analyzed. That somehow are a little more subtle in the usual string perturbation theory framework. Okay, but just to wrap up, again, the main motivation was to try to identify the correct matrix quantum mechanics dual. This, for example, would be one interesting example of a holographic duality between something time-dependent string background and in this case a matrix quantum mechanics theory in one less dimensions. So that would be needed if one could identify what is the correct one. And there's already been proposals, I should say, back in the 90s, early 2000s, which is something hopefully that we can compare to. Okay, and more broadly is another corner in the landscape of 2D string theories and matrix quantum mechanics dualities. And finally, of course, we can take a step back and see if this has interesting lessons for cosmology and QFT or in string theory more broadly. And yeah, as I was saying, as we said in the first thing, there's nothing too special about two-dimensional string theory. This could be, in principle, applied in different string backgrounds, but this was one of the simplest ones that could be studied in detail. So, okay, so let me finish here with this picture that I kind of like. So, thank you for your.
Any questions for Victor?
So, like the graphical equations you wrote in terms of decompositions on different geometries, is that enough to actually fix every coefficient, or?
Yeah, so the hope is that all these constant terms can be fixed through some other means. And in particular, in this case, I hope that they can be fixed by comparing to the matrix model tool. So we still have the full dependence of the energy, so it's a full function. So it's, I think like fixing these extra constants should not be too. There's reason to expect that we can fix those just by comparing to the matrix model.
So what are the conjecture? You said like from the 90s is conjectures of what the matrix model is.
Yeah, so there's been some work on studying time-dependent solutions to, if you're familiar, to the Fermi surface of the matrix quantum mechanics. So even without modifying the potential or anything like that, just the same inverted quadratic potential, there's been studies of time-dependent solutions to those equations of motion for the fermions in the inverted quadratic potential. And there's some interesting ones that, for example, one that looks reminiscent of this is one that in which the Fermi surface start from being fairly flat like this, and it just like evolves into the usual hyperbola of C=1. This seems reminiscent of that one, but I don't have any quantitative evidence for that. But I'm referring to this.
Can you just elaborate on the answer that you gave to Saab about what other kinds of backgrounds can we do here besides 2 dimensions?
Yeah, so for example, you could couple the C=1 Liouville to again 25 free bosons. So you still have a critical background in the sense that the entire central charge of the system is 0, including the ghosts. In principle, you can study that as well. Of course, that has a problem that still has the tachyon, the usual negative mass tachyon. That is not solved by this. But for example, if you could find a supersymmetric version of this C=1, which I'm sure can be done, it hasn't been done in the literature, but I'm sure it can be done because the other space like Liouville CFT, there is a supersymmetric version of that. And then couple it to the usual other 9 directions of the superstring, either 2B, 2A. Yeah, and that will give you something with no tachyon in them.
But it will not look anything like this because you're using the tachyon here.
No, but the weight is still the weight of the C=1 usual this B hat is still negative omega squared.
No, you're misunderstanding me. So
Okay.
Take any field in a superstring.
Yeah.
And you cannot give it an exponential dependence on time and have it be on shell, right? Because
Why not?
well, because it satisfies the equation E squared equals to P vector squared plus M squared with the positive M squared. P vector squared is positive, M squared is positive. So E is real, and you're using an imaginary E for your backgrounds.
Yeah, so I guess what I'm suggesting is that instead of having with the massless case, the superstrings, these guys, plus the Fermi stuff, but instead of having this, you replace it with B hat times E to the I kj xj. So the j now goes from 1 to.
But then some of the KJs are going to be not real, right?
No, so what I don't think so. Is
I mean, the equation is M omega squared equals to K vector squared, right?
Yeah.
That is satisfied here.
So the
So
only
then
thing
you want omega to be imaginary. Don't forget, like the thing called H is some intermediate step in some calculation.
Yeah.
The bottom line is that the mass shell condition is omega squared equals to K vector squared, maybe plus 0 or maybe plus a positive number.
Yeah.
And so if the spatial momenta are positive, are real, and the mass squared is non-negative, you cannot turn on an imaginary energy, right?
So that's
it
what
will
I'm
not
saying.
satisfy the mass shell condition.
Yeah, but this was the same case here, and that was the
No,
point.
here it was not the same. Well, anyway, forget about here. Like, how are we going to do it there? But look, it doesn't matter. This is some detail. We can talk about it separately.
Yeah, sure. I don't think I understand, but okay, we could discuss.
Flipping the sign of the X node connector, just adding the Liouville potential for it.
No, I mean, the whole point of this is that x0 is actual time, right?
Yeah.
So if x0 is time, and you write whatever, like you're in the superstring, you just write whatever you feel like. So there is omega, and there's k vector. And the things are like omega squared, the mass shell condition is omega squared equals to k vector squared plus some non-negative number, right? Doesn't matter how we got there, like what is this h and plus a half, Ramon sector, this. The bottom line is what I said, right? So now omega stands in front of x0, the time, in the formula, or the vertex operator goes like e to the I omega x0, right? And you want that omega that appears in the formula e to the I omega x0 to be imaginary, right? In order to have this kind of picture.
So that's right, but
Where the vertex operator, is exponential with a real exponential and not imaginary exponential. So in the superstring, there just aren't such things, right?
I thought the story here was both in time like Liouville and in the time like free boson. Asymptotically, the operators look in the same way, e to the I omega x0 or chi0, with the weight minus omega squared. Both e to the I omega.
No, but for him, so chi0 was time-like, right?
yeah,
And the vertex operator that he stuck in the exponential, the exponent, behaved like e to the real number times chi0, yes?
I thought it was.
no, it's still a plane wave. So
Wait, okay, so then maybe I just forgot. But then what is this blue region? I mean, it doesn't prevent you from going anywhere.
oh, but the deformation itself of the CFC, it is, as you say.
No, I'm talking about the deformation. I'm not talking about the vertex operators you stuck in
I see
to
your
calculate
question.
correlation functions. I'm talking about the thing that appears in the action.
Yeah.
That thing was e to the
Yeah.
real number times chi0.
Yeah, yeah.
And I'm confused about how are you planning to do this in the superstring? Okay. I mean, there are two separate questions. One is which vertex operators you compute the correlation functions of, and the second is what appears in the action.
Yeah, yeah.
I'm talking about the latter,
Yeah.
not the former. Now, in the critical superstring, I don't know, type 2 superstring in 10 dimensions, you can put whatever you want in the action, but it should be one of those things that appear in the theory, right? So you can say, okay, so I'll stick in there e to the real number times time. And I say, fine, but the thing will still have to satisfy the mass shell condition. And what is that mass shell condition? It's that omega squared is equal to k vector squared plus a non-negative number. And you want that omega, the thing I just called omega, you want to take imaginary.
You're saying in the deformation of the worldsheet action.
This is the only thing we're talking about here.
I thought
Because see, if you're not going to,
it's not a condensate, I think, of the background
so
flat space.
no, I was just asking the question, when somebody says that you can do this in the critical superstring, what do you mean by that? Like, what are you going to put in the action to generate the blue region? That's all I'm asking.
But does it have to be a vertex operator that has a meaning in flat space?
It has to be a BRST invariant vertex operator.
Yeah, so
Because
This
otherwise,
is a different solution.
that's what I'm.
no.
We can't get there by a small deformation.
No. That is out of the. Yeah, I understand what you're saying. That's out of the question because both here. So if you wanted to mimic this structure, here the region in the upper left is a region in which nothing is turned on. And there you can do the same analysis that Polchinski does in his textbook. And so if you're planning to put something that is not in the usual list, I will ask you, how does that something behave in the analog of the upper left region? And what I'm pointing out is that it's okay for it to go like e to the real number times time, with the real number, let's say, being, whatever, negative, so that at large times it goes to zero. But I'm asking about what does this exponential of time multiply? And I'm pointing out that, so he started to write things for us, like it multiplies some e to the ikx, and maybe some crap with fermions, spin fields, I don't know.
I understand. So you're saying because of the upper left region, anything that I add to the action has to be interpretable at weak coupling. Because
Yeah,
in that limit, it maps on to.
Well, that's the whole claim to fame of this setup. You see, if you can ask, okay, what about a situation where nowhere in space-time does it look like a free superstring?
Then
That's not this story. Okay, that's we can talk about that, but this was not the topic of the seminar, and it's not the topic of, by the way, C=1, because if there wasn't a region in phi where it's trivial or it's just a free field with no potential, there would be nothing to talk about. There would not be a DOZZ, and so that's all I'm asking. I'm not. Again, I'm not making any claims. It could also be that I messed up the maths in my head with the jet lag. So if what I said is correct mathematically, then I don't know what you mean when you say I can do this in the critical superstring.
What about like these rolling tachyons that people
So
talk
then you would
about?
want a tachyon in the spectrum, basically, in order to have.
Well, the rolling tachyon starts its life by having a tachyon.
No, but like, people talk about this as being like a deformation of this boundary.
Sorry, you're talking about like Sen?
Yeah, and it's like the
Well, yeah,
opposite.
so Sen, you start with a D brane that has a tachyon on it. You like not with a BPS D brane. You cannot have if you wish in your language, I'm saying that there is no rolling tachyon on a BPS D brane.
Okay, well, all I'm saying is that people talk about this boundary conformal field theory, and the deformation is cosh x0, where x0 is, so it's similar to this, right? It's like
Yeah, so well, we can talk about, well, look, why don't we let people go?
yeah, let's take Victor again.
Whoever wants to. Yeah, in Sen, I think, well, first of all, in that case also, there was the so-called S